Let's talk about nuclear radiation. To be able to define radioactivity, this is when something is going to have something being an atom is going to be spontaneously emitting a ray or a particle. Nuclear radiation is when that ray or particle is coming specifically from the nucleus of the atom. Radioisotopes are when you have an isotope that is going to undergo nuclear radiation. These are often the unstable isotopes. We'll get to that in 25.2 when we talk about the band of stability. Alpha particles, beta particles, and gamma rays are something I want to discuss each one individually and then compare all three, which is kind of the goal of this section, is comparing and contrasting the different types of nuclear radiation. After learning what the types of nuclear radiation are, you can take this in chapter 25.2 and then figure out how to predict what will happen to an atom, specifically a radioisotope. So radioactivity, as I said earlier, is the spontaneous emission of particles or rays from elements. So you see this, radioactive iguana. We know radiation. It's supposed to go through things, show the bones, whatnot. Well, it's not so much that. There's actually a lot more to radiation than that. And it gets a little more exciting. So basically, the atom is producing electromagnetic radiation. So if you remember the electromagnetic spectrum, when there are waves on that are being produced by an atom, such as gamma rays, you have something that is electromagnetically radiating, hence radioactive, because it's actively doing so. Now, nuclear radiation is a specific one we think of the most. It's when you have rays or particles radiated from the nucleus directly. Often if a nucleus is unstable, such as would happen in a radioisotope, which is an unstable isotope, it's going to break down, emitting several types of particles that will lead it to become something that is more stable. So that new nucleus will be more stable and you're going to give off something. So what will you give off? Well, there are three types of nuclear radiation we're going to look at here, and later on we're going to get to another one. So we're going to kind of preview that a little here. The first is alpha radiation, and that's going to consist of alpha particles. And alpha particles has 2 protons and 2 neutrons to make it basically a helium nucleus. And it's going to have a charge of +2. It's going to have a mass of 4 atomic mass units, hence the 4-2 helium. And its common source of that would be something like radium-226. This is when you're checking to see, that's radon, sorry, but radium, remember, it glows and it can undergo this alpha radiation. The penetrating power of this is relatively low. If you want to shield yourself from alpha radiation, just hold up a piece of paper in front of your face, and congrats, your face is shielded. Beta radiation is slightly more penetrating. That's going to be beta particles. Now, there's actually beta plus and beta minus. We usually talk about beta particles in terms of beta minus, which is an electron. And it's going to have a charge of -1. The mass is going to be much, much, much lower than the mass of a single proton. A common source of this is carbon-14, and I'll show you why in a few. The penetrating power of this is about 4 millimeters of flesh. So it's going to get into your skin, but not very far. Again, if you want to protect yourself from this, just hold up like a sheet of plywood or something. Then we have gamma radiation. This is gamma rays, and their symbol is just, well, the symbol gamma. This isn't a particle, so it has no charge and no mass. A common source of this is going to be cobalt-60. You don't encounter cobalt-60 very often, and if you do, you're probably having a lot of problems, because this will go right through a human and mess up all the DNA on the way through. The penetrating power here is very high. You need like a lead shielding, or stand behind concrete, or just stay away from cobalt-60 in general. So let's look at these again. Alpha decay. The nucleus will lose 2 protons and lose 2 neutrons. The total mass will go down by 4, and the resulting atom will be a new element. So here we have 235 uranium. It's got 92 protons, and it's going to lose 4 things total. 2 protons, 2 neutrons, and that's going to be 231 thorium. So it's a new element here. Now, those alpha particles, if they're going to be given off, they can be absorbed by other nuclei, something we're going to get into later. Beta decay is when a neutron is actually going to break into a proton and an electron. And that electron is going to go zooming out of there pretty fast. That's a beta particle. So you have carbon-14, and one of those neutrons is going to undergo beta decay. This will turn that neutron into a proton. Now you see the total mass doesn't really go down noticeably. So nitrogen-14 still has a mass of 14. It's just that nitrogen-14 is very much more stable than carbon-14. So that's going to be that new element, and now that it's more stable, it's less likely to undergo radioactive decay. Gamma radiation often accompanies another form of nuclear decay. Now again, gamma particles penetrate most things. So here you have cobalt-60 turning into nickel-60. It gives off a beta particle, and it gives off gamma radiation. Now gamma radiation just flat out destroys DNA, just shreds it. So this cobalt-60 can actually be used to sterilize things. I mean, if you want to be really rough with it. If you wanted something a little nicer, you can use, ultraviolet radiation.